just recording. So if we had that r took on values in between -1 to 1, what values will r squared take on? So if I take -1 and I square it, it becomes 1. So anything between 0 and -1 becomes positive now. So it's in between 0 and 1. Is everyone okay with that logic there? Because if you take a negative number and you square it, it's positive, because negative times negative is positive. Got it? Cool. So you could also write this: 0 is less than or equal to r squared is less than or equal to 1. So just like we had, if r was equal to 0, there was a weak linear relationship or no linear relationship. In fact, then if r squared is 0, you had the same exact thing as what you had, because if you take 0 and you square it, it's obviously 0. So that means there's still no linear relationship. But if r squared is equal to 1, either it has a perfectly positive linear relationship or a perfectly negative linear relationship. Does that make sense why? Because if r squared is equal to 1, that means r is equal to -1 or positive 1. If it's equal to -1, that means all of the points lie along the line. So the model explains every point perfectly. And then if it's positive 1, it's just a upward sloping line. And still, all the points lie on the line. Easy enough, right? Everyone following that? Everyone online? Do you get what I'm saying? Good talk, good talk. Good stuff. So, what does this coefficient of determination tell us? So, the way we write it, it is the percentage of total variation in the response variable y explained by the linear regression, or the regression line, say that. Due to x. The way that I say it is it's the percentage of variation explained in y by the model. So in this case, it'd be by just the line. That's it. So you know how we have each individual point, how close it is to that line? So the explained variation, so whenever we have, I'll draw something, it'll make a little bit more sense. So say for instance, I have these points right here. And I want to fit a line to them, so it's roughly like that. Agreed? So the variation explained by the model is going to be, so we have each individual residual, so I'll just call it Ri. So we take the square of these residuals and we sum them up, right? That's how we find, that's what we're trying to minimize in this case, is the sum of squares residual. So this line is gonna explain more variation than, it's just like how much the variation in this scatter plot is explained by this line compared to if we didn't have a linear trend of the data, then based on what we said last time, the best prediction for y is the sample mean. So then this will be the total variation, will be each individual y value minus the mean and then square that. So that value is going to be larger than this. Does that make sense? Why? Because there's more variation from this line down to here for each point. So that means the total variation is going to be larger than this variation. So we're trying to explain this total number of variation right here by turning it and making it into a line. Does that make sense? Does it? Okay, that's what we're trying to do. Yeah. So with that ratio, we can find r squared. So in a different class, they'd probably ask you to find one of these two, but I'm not going to do that. Your calculator gives you the answer. So that's what I expect in an introduction level class. So if we have the coefficient of determinant, oh, I just said this earlier. So I literally said that earlier. Note, if r squared is equal to 0, the linear regression line cannot explain any of the variation in y because there's no linear trend because r is equal to 0 in that case. Everyone okay with that? And then if r squared is equal to 1, again, that means that r is equal to positive 1 or negative 1. And then again, all the points lie along that line. So that means the regression line explains 100% of the variation in the response variable y. Does that make sense to everyone? Because if every point lies along that line, the explained variation over the total variation is just going to be the same. Is everyone okay up to there? So, from our previous example, we had what is the coefficient of determination. So, we found that r was equal to negative 0.944. Does everyone remember how to find that value in your calculator? Or do I need to show you? Okay, I'll show you again. So, I'm going to have to look at the example and remember what it said. Wait, I think I still have it. So, in L1, we had the number of absences for a given student, and in L2 was the corresponding final grade. So, to find that value of r, we go to stat, test, or is it test or calculate? It's test. Yeah, test, and then go down to option F, hit enter, and it'll tell you where your values are. So your x values, which are the number of absences, are in L1. And then in your L2 are the responses, the final grades. And the frequency, just leave that as 1. And then this right here is the hypothesized y-intercept and slope. So in this case, they're both equal to 0 under the null hypothesis, and we're testing whether they are not equal to 0. So just leave that as not equal to 0, and then hit calculate. So it'll tell you the t-test statistic that we actually calculated earlier. For this t-test, it tells you the corresponding p-value. Also, it tells you A, which is the y-intercept, B, which is the slope. And then it also tells you r and r squared. So if I give you a data set on the final exam and I say find r or r squared, all you do is enter in the x values into one list, the y values into another, and then run that linear regression at t-test on them, and it will give you everything you need. That makes sense to everyone? I think it's a lot better than having to use that formula. So that's how you do it on the calculator. So then based on that r squared, so we just took that r value we got from the calculator and squared it. So that tells us that r squared is equal to 0.891. So 0.891 as a percentage is 89.1%. Just move the decimal over 2 places to the right. So then we can say that the regression line explains 89.1 of the percent of the variability in Y. So in this case, Y is final grades. Does that make sense to everyone? It's just plugging in that percentage into the interpretation of R squared. That's all it is. Everyone online, you following so far? Okay. So now that we have the coefficient of determination, we can have the coefficient of non-determination. So it's just the opposite of the coefficient of determination. So it can be found by taking 1 minus R squared. So it's just the complement of R squared. Does that make sense why that is? Yeah. So determination is the opposite of non-determination. So I just take 1 minus the determination to get the non-determination. So I'm pretty sure on the final exam there will be a question about both of those. So know how to calculate them. So what does the coefficient of determination tell us? So if the coefficient of non-determination tell us actually. So if the coefficient of determination told us the percentage of variation in Y due to the model in X, then we could say the coefficient of non-determination tells us the percentage of variation in Y not due to the variation in X. So it's basically the percentage of variation in Y not due to the regression line. Again, it's just the opposite of what the other one was. So the other one said the percentage of variation in Y due to the variation in X. This one just says not due. So opposite again. So not due to the variation X, you mean? So let's see how to describe this. I don't know how to describe it really. So due to the variation X, so that means as X changes, we're attributing the percentage of variation in that Y, and that's R squared. So the percentage of variation not attributed in X is the variation in our response Y that is not explained whenever we move our X's. Does that make sense at all? That's kind of what it means. I don't know how to explain it very well, but that's what it means. I don't know how to describe it. That's just what it is. Trying to think. Okay, I see what I think. I've got an idea. So how we had this right here. So we had our linear regression line, and then we had just the predicted value not using the regression line. So this R squared is the variation explained by this line over the total variation of this line. So then the coefficient of non-determination tells us the variation in this compared to this that cannot be explained by the line. That's what it is. That's kind of graphically what it means. So it's the variation not attributed by this line. What's up? Yes. Yes. Mm-hmm. Because we can't draw a perfect line to every data set. Does that make sense? Because every point is not going to lie across that line. So based on that definition and our previous r squared of whatever it was, 0.891 or something like that. So then from the previous example, what is the coefficient of non-determination? So you just take 1 minus r squared. Easy enough. And that's 1 minus 0.891, which is 0.109. So, and then you can interpret it with that definition up there and just plug in the percentage in this case. So 10.9 of the total variation in final grades is not due to the variation in the number of absences. So in this case, I just plugged in what is y in this case and what is x. Y was final grades, x was the number of absences. Okay, so that's the end of chapter 10, besides your review thing. That's at the end. So let's look at this, and then we'll take a little break, and then we'll review. So this one says, a study is conducted to determine the relationship between a driver's age and the number of accidents he or she has over a 1-year period. The data is shown below, along with the calculator output. So in this case, here we have the driver's age and their corresponding number of accidents in a 1-year period. And then over here, we have the output from your calculator. So the first thing says, define the independent and dependent variables in the study. So it's basically asking what is being changed and what is being measured. So what is changing in this case? So the age is going to change. So we're sampling different age groups. And then we're measuring the number of accidents. So the independent variable is age and the dependent variable is number of accidents. That makes sense why that is? Okay. So what does the correlation coefficient tell us about the relationship between age and number of accidents? So if you go up to the output, you'll notice that R is equal to a negative 0.77. So that means that it's kind of close to -1, so there's a relatively strong negative linear relationship. So what does that mean? As you get older, the number of accidents you have goes down on average. Does that make sense to everyone? So the next thing says test the significance of rho at a significance level of 0.05 and use the table I. So what is table I? It's those critical R values. So if the absolute value of R sample correlation coefficient is greater than the actual critical R value, then we reject the null hypothesis and we can conclude that there is a significant linear relationship. So how did we do that last time? So the first thing we did was identify the two hypotheses, the null and the alternative. So the null being that rho is equal to 0, so there is no linear relationship between the two variables. And then our alternative hypothesis being that rho is not equal to 0, so there exists a linear relationship between the two. So then we go to our decision rule. So we reject the null hypothesis if the absolute value of R is greater than 0.754. Does everyone remember where I got that 0.754? Or do I need to show you? That's just how it is in simple linear regression because there's two variables we're using. There's driver's age and number of accidents. So we have to take both of those variables into account. So that's why it's n-2. Dang it. I left my tables at my house. So, where is it? Trying to find the table so I can show you all how to find this thing. Everyone online, do you remember how I got that 0.754, or do I need to show you? Okay, so let me share my screen real quick. Yes, basically. If it's close to 0.5, you could say the relationship is moderate, so it's close to strong, but it's not as strong, like not too strong. That's the word most statisticians use, is moderate. And then if it's below, like 0.4 to 0.3, we say it's weak. Okay, let me make sure I'm showing the right thing. Yep, good, we're good to go. So the critical values can be found on the last page of your table packet. So it's these right here. The critical values for the test. I don't know what PPMC means. I'm pretty sure it's Pearson something. So, and here it says reject the null hypothesis if the absolute value of R, our sample correlation coefficient, is greater than the value given in the table. So these values are for a two-tailed test. So in this case, we're only going to do a two-tailed test for rho. Oh, crap, I forgot. You're on the document camera. There we go. Thank you. So there we are. So this is the last page of your tables packet. So on the exam, you will get this. So here it has the degrees of freedom, and up here it says note the degrees of freedom is equal to n minus 2. So be careful. I will put a one where it has the degrees of freedom as n minus 1, and then I am going to pick one of those answers as the critical value for the test. So make sure you know the degrees of freedom is equal to n minus 2. So we had, what was the degrees of freedom? Oh yeah, it was 7 people we had in the sample. We had like A, B, C, D, E, F, whatever it was. So we had 7 different students, and we looked at their number of absences and final grades. So if we had 7 students, then the degrees of freedom is equal to 5 in this case. So we go to 5, and we're doing an alpha is equal to 0.05 test. So that means 0.754 is our critical R. Everyone online understand how I got that? Everyone in class understand why? What's up? Yeah, what's up? Yes. I can, if you want me to. Yeah. I'll look at back an example in chapter 8 and 9, and I'll show you how to do it. We have to have it data, though, because if you don't have data, the calculator won't do it. So. Okay. That was loud. So, there. So, that's how we got this 0.754 here. So then our decision rule for this test is reject the null hypothesis if the absolute value of our sample correlation coefficient is greater than 0.754. So we calculated, or we actually are given the test statistic, in this case, the R value. So R is equal to negative 0.77 here. So that means the absolute value of R is equal to 0.77. So it is taking that negative away. So, and 0.77 is greater than 0.754. So therefore, using that decision rule up here, we have reject the null hypothesis since the absolute value of R is greater than 0.754. And then we can conclude there's a significant linear relationship here. If you want to write it in the words of the problem, you can say there's a significant linear relationship between the driver's age and the number of accidents. Is everyone okay with that? So, and then the last 3 or 4, whatever parts it is. So it says write the fitted regression line. So it's just asking you. So you have the regression line y equals a plus bx. You're given a and you're given b. So can you just write the prediction of y from that? So using that, we have that y prime. So this is just the prediction is equal to a. So that's 11.86. So I just rounded to 2 decimal places. And then minus 0.35 times x. That's it. And you can find these right here in your calculator by doing what I did earlier. Just running that linear regression t-test and identifying what is x and what is y. So then it asks you, predict the number of accidents a 31-year-old might have in a 1-year period. So in this case, that means x is 31 because x is the corresponding age. So then just plugging that into the formula, we have y prime is equal to 11.86 minus 0.35 times 31. So we plug that in your calculator, it ends up being 1.01. So that means a 31-year-old on average has about 1 accident per year. If you have 1 accident per year, please don't drive near me. Everyone okay with that? You just plug in the number. So, what does the next thing say? So predict the number of accidents you might have in a 1-year period. So that just means take your age and plug it in for x. So in my case, that would be 11.86 minus 23 times 0.35. If you're curious, I'm 23 years old. So I'm not much older than most of you. I think there's actually a student in the class who's older than me. So that's how you do that. What are they doing? Please stop. So, and then I say what's the coefficient of non-determination. So you were given that r is equal to negative 0.77. So just take negative 0.77 and square it. You get 0.59. So that's all I asked in that part. So, is everyone okay with all of that jazz? I'm gonna kill them. So, we're gonna take a little break because I'm tired. And we'll come back and review. What's up? What's up? What about it? No. That's a completely different one. Okay. Can you hear me now, people online? Okay, sorry about that. I guess because I didn't have this thing on, and I don't know if it connects to the computer or not. So, sampling techniques. So you need to know how we get a stratified sample. So, does anyone remember how that is? So I divide the population into different categories, which are called stratum. And then from each of those different categories, I take a random sample. So, say for instance, if I divide the population of OSU undergraduates into those who are in Greek organizations and not in Greek organizations, and then I take random samples from both, that is an example of a stratified sample. Hint, you may see that on the final exam. That may be the first question on your multiple choice section. So, in a cluster sample, what do we do? So, in a cluster sample, we can literally, so we take certain, say you want to take a sample of certain cities and see what the average income for each city is. So you can literally just take like Oklahoma City, Tulsa, Stillwater, and then you can take all of those individuals as a cluster and then calculate, say, their mean income. So that's an example of a cluster sample. So then a random sample means, does anyone know what that means? It means each individual in the sample has equal probability of being selected. And then systematic is whenever I take every case member. So say I took every 5th student in this class and I looked at their final grade, that would be an example of a systematic sample. Is that making sense to everyone? Everyone remember that stuff? Okay, so I'm going to try to remember what the next way I want to describe the next thing we do is. I can't remember how I described it in chapter 1, and I don't want to confuse y'all. I can't remember if I called it levels of statistics or what. Levels of measurement. So, anyone remember what those are? So that's when we had 4 different levels. We had nominal, ordinal, ratio, and interval. So nominal, it was basically just categories, and then we were sorting certain characteristics into different categories. So then ordinal, so we're still dealing with categories in this case, but there is a order to them. So for instance, if you have like your evaluations that you have to give me, you have strongly agree, strongly disagree, and you have a scale. I would prefer you put strongly approve or whatever the heck it says. I don't know what it says. But some of you won't, I know. I got like 2 negative reviews last semester out of 24. So I was pretty satisfied with that. So ordinal, interval, and ratio. So interval is, it's on a numerical scale, and there is no true zero. So you could talk about like Kelvin or something like that. Like that's a scale. It involves numbers, but there's no absolute zero, I don't think. I don't know, I haven't taken chemistry in 5 years, but that's one that came to my head. And then ratio, so it involves quantitative measures, so numbers in this case, and you can compare those numbers. So say you could talk about the age of students in this class, the difference in those ages. So the maximum age difference in this class for me compared to you is probably 5 years if you're 18. Some of you may be closer to my age. So if I see you at a bar, please don't say anything. I went down to the Strip one time and I was like, oh my God. Never went again. I don't like going out much. I'd rather stay at home with friends and play beer pong, not be at a bar with a bunch of drunken dumbos. What? Oh, someone said mood. David said, I take offense. No invite. They're trash talking me online. Hey, remember, I grade your final exams. I was gracious on grading parts of exam 3 or exam 2. If you messed up on one part, but you got the rest right based on that part, I gave you credit. If you didn't do it, I didn't give you credit. Now Colton is saying something. What is he saying? So, next thing, what does it say? And do statistics, you mean what? Colton, I don't understand what you're saying there. So, those are the levels of measurement, so know how to identify. So, if I say, in the survey, John and Ann would like to ask about the name Joshua, that's my name, their statistical consultants suggest the following question. Do you strongly approve, have no opinion, disapprove, or strongly disapprove of the name Joshua? So then you identify what kind of measurement that is. Based on that, what do you think it is? Ordinal, correct. So, what else? Let's think of something else. How did I describe it in chapter 1? So, different types of variables. Meaning, what are qualitative, quantitative, continuous, and discrete. So, qualitative variables, you could talk about like hair color, eye color, stuff like that. So it's like a characteristic. Quantitative are numbers. So obviously you could say like your percentage in this class is a quantitative variable. The number of people in this class is a quantitative variable because I can count. Right now there's probably like 13 students out of 72, which is not good, but there's quite a few online, which is good, at least they're online. Some people just aren't here. So continuous, does anyone remember what that means? It can take on any value in between any two values. So that's what that means. And discrete means you can count the units of measure. So a discrete variable in this case would be the number of students in this class right now. I can count you. So does that make sense? So that means that continuous variables and discrete variables are actually still quantitative variables. So if you look back in chapter 1 notes, we will show that we broke it down for types of variables were quantitative and qualitative. Under quantitative, you could have continuous or discrete. So The next thing it looks like is, what did I see? Okay, this is back to chapter 2. Okay, so we talked about this when we were creating frequency distributions. So whenever we made a frequency distribution, when we made a graph corresponding to it, so say we had a histogram, and we had to allocate a certain class width. Does everyone remember that stuff from chapter 2? A long time ago. So, know how to compute the class width. Does anyone remember how to do it? So, the class width is equal to the range divided by the number of classes I asked for. So, does anyone remember how to find the range? Okay. The max minus the min is the range. And then still divide that by the number of classes. So, does anyone remember what happens if this ends up being a decimal? Yep, if it's a decimal, round up. It doesn't matter if it's like 7.1, round up to 8. So, you should know how to do that. You should also know how to identify what type of graph it is. So identify types of graphs. So does anyone remember any of the types of graphs we talked about? Those are the shapes of the graphs. We will talk about that. There's a question on here about the shape of one of them. So, yes, histogram. Bar chart or bar graph, however you want to call it. Time series. What was that one I want to talk about? And pie graph. Or pie chart, I'll say pie chart. Know how to identify those. So there is something called a Pareto and an ogive, but I really don't like those, so we're not going to do that. We'll make it a little bit easier. So that's chapters 1 and 2 so far that I think will be helpful. What's the next chapter? 3? Anyone remember what chapter 3 covered? Because I don't. Let me look. As you can tell, I didn't come prepared. Whoops. Sorry. I'll come more prepared next week if I have time. I have homework due on Monday, and then I have another homework assignment due on Monday. So I'm going to spend my weekend doing homework, and it's going to suck. Oh, that's easy. Okay, so chapter 3 was about statistics. So, does anyone remember some of the statistics we talked about in this class over the last 14 weeks? Yeah, so we talked about the sample mean, know how to calculate that. So, the sample mean. Does anyone remember the symbol for the sample mean? Correct. And what is X bar used to estimate? The population mean mu. So we have the sample mean. What else do we need to know how to calculate? Let's see. Okay, another thing we talked about was the midpoint. Does anyone remember how that is? So you just find the number in the middle. That's all it is. So there were different, well, yeah, midpoint. Oh, median midpoint. So yes, in this case. So the definition I gave you says the median is the midpoint of the data set, so just the number in the middle. Yeah, I've almost tried to talk about mid-range, which is a different thing. So that's a measure of variation. Right now we're talking about measures of center. So the median, if you enter the numbers into your calculator, it will obviously give you the median. If I give you a list of numbers, so if the number of digits, or like the number of numbers in there is odd, then the midpoint is the one in the middle. Does everyone remember that? So if I had 5 numbers, the midpoint, or the median is going to be the third number. That's if you put them in order. You have to make sure they're in order. So then if it's even, you take the average of the 2 most middle numbers. So what else? We talked about the mode. I'm pretty sure there's a question on there about the mode. Anyone remember what the mode is? Yep. Most often in a data set. So, and then, does anyone remember how the mode relates to the normal distribution? So it's unimodal, it's symmetric about the mean, basically. So if there are 2 values that occur with the same frequency in a data set, we call that bimodal. So I'm pretty sure on exam 1, I gave you a true and false question, and I said something with more than 2 modes is bimodal, and that was false. It should be multimodal. That's what they call it. Okay, I don't know if I'm going to talk about that. So does anyone remember how to find the mid-range? It's another rough estimate of the number in the middle. You just take the highest value, add the lowest value, divide by 2, but I don't think I'm going to put that on there. The weighted mean, that's not going to be on there. I don't want to mess with that. Okay, we already talked about the range. Okay, I don't think I'm going to talk about that either. No, I don't want to do that either. There's a lot of stuff we're not going to cover on this final exam, fair warning, so it's kind of good. I'm just going to try to cover the easy stuff. I'm looking at this chapter 3 completed notes, and I'm like, we did a lot that I'm not going to do. So. Oh, one thing you do want to know, though. 5-number summary. Does everyone remember what that is? Okay, so I have the minimum, first quartile Q1, the median. So does anyone know another name for the median? Q2. So we just say the median. Q3. Then the max. So if I give you a 5-number summary of something, you should be able to identify what is Q3, for instance. So just the number in the 4th slot. What's up? There is, but I didn't make outliers in this one. Yeah, so there can be outliers, yes, but will I put on the final exam? No. That's too much to remember. Okay, so that is what we will cover for today. And then next week, we will continue on. We will talk about chapters 4, 5, and 6. So 4 was about probability. So there will be some probability questions on there, maybe 1 or 2. 5 was about discrete distributions and frequent, something else like that. 6 was about the normal distribution. But we'll pick up there next time.